section 11.2 is all about truth values, okay? And what is all about truth tables. And what we're going to do is we're going to learn how to use the truth values of P and R, P or R, and not P. And we're going to see how those depend on the truth values of our original simple statements. So here's what we're going to cover in this section. Remember that a statement form is an expression formed from simple statements and connectives according to the following rules. So a statement form is an expression formed by simple statements. A simple statement is in statement form. Okay, that's true by the definition of a simple statement. If P is a statement form, so is not P. And if P and R are in statement form, so are P and R, P or R, and P implies R. So here are some examples. This question mark here, I don't know what that was supposed to be. I think it's supposed to be an arrow. So just ignore this half. Okay, so these are examples of statement forms. And we're going to use something called propositional calculus in order to find the truth values of these statement forms. So propositional calculus is the manipulation and verification of logical statement forms. So we're going to use truth tables and tree diagrams. Not really tree diagrams so much, but primarily truth tables, okay, are going to be used to determine the true values of these statement forms. So when we start with a truth table, like let's consider our statement P. This is our simple statement. It has one of two truth values, okay? It can be true or false. And we can list all the truth values of P in a table. So P is either true or false. When we're constructing a truth table, it needs to include a column for each simple statement, a column for the compound statement, a row for each possible combination of truth values, and a column for the statement form. The column for the statement form has its truth value, which depends on the simple statements. Okay, so the simple statements influence the truth value of the compound statement. So let's look at the truth table for not P. Okay, so I have my truth value. I have the simple statement P. I have P is either true or false. Okay, the statement form of P has the opposite value of not P. Okay, this is how we would read this, not P. So if P is true, not P is false. If P is false, not P is true. They have opposite truth values. Let's take a look at our next conjunctive. So here's the truth table for and. So the statement P and Q has two simple statements, P and Q, and it's connective and. Remember that when we use the and symbol, that's called the conjunction. And it's important to note that P and Q is only true if both P and Q are true. So let's take a look at how I set up these first two columns. So for P, I did true, true, false, false. And for Q, I did true, false, true, false. Now, why did I do that? I want every possible combination of true and false for P and Q. Okay? So they could either both be true, P could be true and Q could be false, P could be false and Q could be true, or they could both be false. So then I remember the rule for the conjunctive P and Q, and it's only true when both are true. So here I have P and Q is true as long as P is Q and true is Q is true. And then I have false values for the rest because one or both of them are false. Okay? So that is how we use and. When we're looking at or, which is the disjunction, right? I have P or Q. P or Q is true if either P is Q true, Q is true, or both P and Q are true. So what does this mean is only one or at least one must be true. So again, I set up my truth value for my simple statements P and Q. I do true, true, false, false, true, false, true, false. This is so I can set up my table. And P or Q is true as long as I have one true value in P or Q. So true and true gives me a true, true or false gives me true, false or true gives me true, and then double false gives me false. So this is quite different from and. So why don't we go ahead and practice making our own truth table for PQ, P and Q, P or Q, and then not P or Q. So for my first column, I'm going to do true, true, false, false, true, false, true, false for these simple statements. So as you can see, each simple statement and compound statement has a column. So P or Q, I only need one of them to be true. So true and true would be true. True or false is true. False, that's a terrible looking F. There we go. False or true is true. And false is false. Now I'm interested in not P or Q. Not is the negation. So it's going to have the opposite value of this column right here. So instead of true, I have false. Instead of true, I have false, false, and then instead of false, I have true. So here is the completed truth table for not P or Q. I put in the slide so you can double check your answers. Let's do one a little bit more complicated. I want us to get really comfortable with constructing these truth tables. So I want to know not P and not Q or P. So we got to break this down into the tiniest little parts. So I know I've got P and Q. I've got not Q. I've got P and not Q. And I've got not P and not Q. So I started the same way. Okay, so my first column is not Q. So not Q is going to be the opposite of Q. So instead of true, I have false. Instead of false, I have true. Instead of true, I have false. And instead of false, I have true. Next, I want to know P and not Q. Remember, and is only true if both P and not Q are true. So here I have a true and a false. That's going to, maybe I should switch colors. So here I have a true and a false. That's going to give me a false. Here I have a true and a true. That's going to give me a true. Here I have a false and a false. That's going to give me a false. And then I have a false and a true. That's going to give me a false. Because remember, they both have to be true. So I only have one true value in this column. The next thing I need to know is not P and not Q. So this is going to be the opposite of this column. So I'm going to take the negation. Instead of false, I'm going to have true. Instead of true, I'm going to have false. Instead of false, I'm going to have true. Instead of false, I'm going to have true. Now I have my final compound statement. I have not P and not Q or P. And remember, or is true as long as one or the other is true. So let's take a look. Okay, I have true and true, which is going to be true. True or false, which is going to be true. False or true, which is going to be true. And then false or true, which is going to be true. This is really interesting. I have all true statements. This statement is always going to be true. This is an example of a tautology. Let me say that again. Tautology. A tautology is a statement form that always has a true truth value regardless of the variables before it, and we denote it with a T. A contradiction is kind of the opposite of a tautology, right? A contradiction would be a statement form that has all false truth values, and we would denote that with a C for contradiction. Here's the formal statement definitions for tautology and contradiction. The next topic I want to talk about is the exclusive or. It's denoted with this symbol that's like a 0 with a cross through it. This statement of P or Q and not P and Q is how we define the exclusive or, okay? And we're going to get that it's false whenever it has both the same value. So if I have true, true, I get false. True, false, true. False, true gives me true. And double false also gives me false, okay? So why don't we go ahead and prove the exclusive or? This is one of the least common conjunctions we're going to use. One of the least common combining symbols we're going to use, but I want us to prove it. So let's prove how we got from here to here. So again, I'm saying that these are equivalent. I don't know why I have another column for P. This is kind of unnecessary, so we're going to skip that column. Okay, so the first thing I want to do is fill in my truth values. True, true, false, false, true, false, true, false. So P and Q is going to be, P or Q is going to be true, 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 false, because only one or the other needs to be true. P and Q is going to be true, false, false, false. Next, I need to know not P and Q. That's going to get me, it's the negation of this column here. So I'm going to have false, true, true, true. Now I have and. So I need both of them to be true, or I need, that's it. It's only true if both of them are true. So here, I'm not looking over here, right? I need to look at these two columns. I need to look at P or Q and not P and Q. These are the only two columns I'm looking at. So true and false gives me a false. True and true gives me a true. True and true gives me a true. And false and true gives me a false. So as you can see, we figured it out. We have proved the exclusive or.